So, welcome back to part two of the Capstone presentation by Curtis Goodwin. To quickly reiterate the last point of emphasis of the part one presentation, we want to talk about the EPA value and how that was used to assess the transition from one play to the next as being positive or negative. And if we remember from earlier, EPA does represent an assigned point value where 0 is the middle needle, and so anything positive of that would be a positive play, anything negative of that would be a negative play. And using that as a transition expected value that would be stored to assess all positive plays and all negative plays uh, given what we've seen previously. And so this will be further explained once we get into the model. The next component would be to create two random variables that would store expected values for these, and then to also associate the expected yards gained in a separate random variable for both pass and run plays, given that we've seen a positive play or given that we've seen a negative play. One tangible example would be if it was 2nd and 10 and the quarterback throws an incomplete pass. Obviously, that would be a negative EPA. And so given the last 4 years of play-by-play data for each team on pass plays that were negative, what would be the next expected play, both with what's the percentage of run versus pass, and then if we were to pass, given a negative play was seen, what's the expected yards gained on that passing play after a negative play occurred. And so that would be a tangible example, but we're going to talk about some of the methodology first. The model does utilize probability density functions, and so what was looked at was in each random variable, we pulled out those distributions and we customly fit the best, most common probability density functions. So these are not all normal, some were skewed. So we included beta, gamma, chi-squared, normal, Weeble, and exponential. Also inverse gamma to be flexible so that we get the best probability density function based on the distribution for each variable. The nice thing about the probability density functions when it comes to simulation is that unlike what we did with the discrete, we're able to pull out continuous values between a probability of 0 to 1 of all possible future occurrences that are modeled based on historical data. And so this allows for infinite number of runs in the simulation without running out of combinations. One visual of this would be if we use the Python function random.random, which returns a random number between 0 and 1, which would represent a probability, you can use the inverse CDF to then pull out a correlating x value, and let's say we're looking at passing yards, then it's going to give me a passing yards based on the model, the function model, which is based on the historical data that we're observing and we stored in that particular random variable. And so if you think of having a bunch of these distributions that represent our variables, given a scenario, then we can accurately sample continuous x values that could possibly happen in the future, and they're modeled based on the historical data. So we'll spend more time on that. But moving on, to set up the elements of a simulated game, this actually looked at setting up elements of an offensive drive. The first components of the drive would be your starting field position and then the number of plays you were going to have on that particular drive. And then from there, we would start the Markov chain process and start looking at predicting expected yards gained, whether through the pass or the run, and then observing positive or negative changes and using those random variables to predict, given X number of plays, this is how many yards will be gained on this offensive drive. And over a designated number of offensive drives, you would have an outcome score for each team in the simulation. So we've talked a little bit about what a Markov chain is, but to give a visual, to predict a future state given a present state, if we look at the number line and we look at the plays in sequence, so from play 1 to play 2 to play 3, all the way to play I, and we want to predict play J based on what we saw in the transition to play I, this would be a little bit what it looks like. So if we have a positive transition from play 1 to 2, so a positive play occurred, and again that's evaluated based on the EPA value of the play, then no matter what occurs from play 2 to 3, we're going to store that value as our positive random variable, which I called y up. And then likewise, we're going to observe the next transition. So from play 2 to play 3, if it's positive again, regardless if it's negative on the next play, we're going to store that in the positive random variable. And so what we're doing is we're going back, almost looking back kind of in our crystal ball. We'll say, okay, what happened on the previous play? And then on the next play, we're going to start storing those values as positive random variable or a negative random variable. And then once we have those stored, we can split them up and see how pass plays and how run plays were split up inside those expected values of the random variable. I do want to make one note with this technique, and the stock market is probably a better way to think about this. Just because a positive play was observed on the previous play, that does not mean that a positive play will occur on the next play. So there is a situation where y up could have a negative expected value. If you think about the stock market and you're looking at day-by-day data, a lot of times when stocks trend up, people sell. So sometimes you'll have a situation where the positive random variable, the y up random variable, while it's looking at all of those previous positive trends, it could contain a negative expected value because now people are selling and going down. The same could hold true in football. So if there's a real positive play, which we're going to see later, maybe there's a good chance that it's a running play next and the actual expected value goes down. And then likewise, just because we observe a negative play does not mean that the predicted expected value of the next play is going to also be negative. And so looking at this from a holistic standpoint, I ended up only using 2 years of data, but that was enough plays to give a really good idea of what will happen given we've observed a negative play and what will happen given we've observed a positive play. Really quick, the reason that 2 years of data was used, even though 4 years of data was scraped, is that because this was tailored to the Houston Texans, Deshaun Watson has only played 2 years of healthy football, and so I felt that the quarterback is enough of a valuable player to a team, and we're focusing on the offense, that if we were to include that third and fourth year, it wouldn't be representative of their performance now that they have a higher caliber quarterback leading their team. So here's an idea of what the data frame that was created to store these random variables looked like. So if we look at from play 0 to 1 on the index, right, we start with a 0 EPA on play 1, and when we move to play 2, we observe a positive value in the EPA. So no matter what, on the second play, the next play, we're going to store that value, and we're going to store that. I couldn't call it Y up for both teams, so I called it Texan up and then Texan up yards. So here is the stored EPA value, and here's the associated yards gained value. So on the next play, we had a negative EPA, but that still gets stored in the positive random variable, and then the yards associated are stored with that. So now when we look at the transition from play 1 to play 2 in the blue box, that's negative. So no matter what, on the next play, we're going to store whatever value we observe in the negative random variable. And again, The Texas down represents Y down, and that's going to store the EPA value. And then the down yards is going to store the expected value of yards gained. So in this particular scenario, no yards were gained, and so on and so forth. And we did this for 2 years. So understanding the structure of how we were getting our expected values, here's some really interesting statistics. So when we split up the positive, the Y up, and then the Y down, both for the pass and the run plays for the Houston Texans, you can see the amount of each. And so the analysis was after a positive play was observed, then the Texans passed the ball 47% of the time compared to 52% of the time running. However, when a negative play was observed, they're almost twice as likely to pass as they were to run, which that can be pretty useful if you're scheming for a defensive scouting team. Likewise, with Green Bay, the negatives were similar. They passed twice as much as they ran the ball, given they saw a negative play. However, Green Bay passes the ball a lot because if they observe a positive play, they still pass at 60%. What is interesting is that under pass plays, you can see what our mean EPA value is, and so it dramatically is increased based on if they saw a positive play, contrary to it's very low if they pass the ball after a negative play. So even though they pass the ball a lot, their probability of a successful passing play is dramatically more given that a positive play occurred before. This could be in part because Green Bay employs a hurry-up offense and Houston Texans do not. So here's a quick map of what the simulation looks like. So you have a random draw from field position based on a probability model. And then you also have a random draw of the number of plays based on a probability model. And these models were actually distributions of the field position and the number of plays per possession for each team. And so we randomly select this, and here's our starting point. And then I gave a 50-50 chance to either start with a positive or a negative play, because the first play has to start with some type of EPA. And once you have that first play, now we're going to draw from one of these two distributions, either the positive change random variable, that's the positive EPA, or the negative EPA random variable. And the change will occur based on what the expected value was. So for example, if I observe a positive play, I will draw from the positive distribution. If I pull a positive play from that distribution and my expected value is positive, then I'll draw again from this distribution. If I pull a negative play, I'm going to switch and my next play draw will come out of this. When I draw an EPA from this, I'm also going to draw an associated, and we're going to split by percent, which we observed in those summary statistics, pass run. We're going to draw the expected yards gained given a pass or a run play, and that will be the yards that we subtract from yards to go. So, tangible example, if I had 80 yards to go and I was given 7 plays on the draw, I would continue to draw this 7 times, and I would start subtracting the yards, the expected yards per play given a negative or a positive play had occurred, and I would subtract that from yards to go, and then at the end we had a way of tracking this. So we ran 2 segments of data through this model, and here are some results. If we ran all of the data home and away for the Green Bay Packers and the Houston Texans were expected to win. The point spread was 0.91 in favor of the Houston Texans. They had a 65% win probability, but the expected points were not in their favor. However, if we drill down further, because the game is going to be played at home for the Texans, we utilize only home data and only Packers away data. You can see how all metrics improve in the Texans' favor and their win probability increased by 11%. Expected points are now in their favor. 2 really quick takeaways. Simulation models predicted more accurately than traditional models. They did better with the outliers and handled multiple unknowns more accurately. Additional simulation models would want to include player value and roster movement, as that's very critical to accuracy. Thanks for